Okay, this is lecture 31 on invariant maximality by Harvey Friedman, please.
Thank you. So I have some really good news. I think that I've multiplied by a small integer the dedicated readership of this. In other words, people who will do more than just look at the title and the table of contents. Um, the bad news is that I didn't do this quick enough during the last week to really give you a lot of meaty details about the biggest advances, but that will have to wait till next week. Things are stabilizing rapidly now in this book. This was a hanging issue that was annoying for a number of reasons. It wasn't nearly fatal, but it was annoying. So basically, well, I'll go through this and tell you what happened. Okay, so uh, once again, so there'll be a lot of repetition from last week, but notation and terminology have changed. The biggest results have sharply improved and so forth. Um, okay, so uh, yeah, the chapters have changed and added again, but not because of any spin of any uncontrolled expansion of the book. So the book starts off with the introduction, which of course could not be written even today, um, and then there's this major chapter two that we're talking about. By the way, all of the old book is right here. This is the old book. Uh, that we spent a very long time on. That's all here. And this is the new book, the new front book. In other words, the book is really got two parts in some sense. All right. So this chapter that we're dealing with, as we did last week, but it's now greatly upgraded, is called N shift, N equivalent, invariant maximality. And I say derivations. Um, um, okay, I forgot. Okay. I don't have the chapter. Here we are. I'm sorry. I'm sorry. This is what I wanted. N shift, N invariant. This is N shift, N equivalent. Okay. N equivalent, uh, invariant maximality reversals. Sorry. This is what I meant. Yeah, there we are. Okay. So there's a new chapter added, which is a new reversal. I was spending a lot of time trying to make sure that there's only one reversal in this book, only one reversal in this book, this giant one. And there is going to be two. This one is much, much easier than this one, than this one, which used to be chapter four. And in fact, I'm almost certain I'm going to be able to reuse a lot of this in here, a lot of this in here. So this is not going to be, of course, this is going to be treated as if see chapter three. So some of this will be repeated in here, and then it won't it'll be stated that I did this or that in chapter three, and you can redo it here or something like that. But so this 3 plus 8 is going to be very close. I'm not 3 plus 8, 3 plus 7. 3 plus 7 is going to be pretty close to just the old seven. If in terms of complications. 3 plus 7 is about the old seven. All right, well, the old chapter four. Uh, so finally, I realized. So what is going on here in terms of the reversal? Well, this is any shift and any equivalent invariant maximality are the same. These two are the same. We proved this the equivalence actually, but they're both very important and intuitive. Um, the point is that this invariance that we're doing in the lead of this book, in the front part of this book, this invariance is much stronger than the invariance that we were doing in local invariant maximality. Um, this is much stronger, so reversals are much easier. And the revelation that I had earlier was that this much stronger invariance is really the most mathematical of all my invariances, as we've been talking about the last 2 weeks, the last couple of times. That was the impetus to change the book this much. That these invariance notions, these two, are the most mathematical, and they're much stronger in spirit. Everything's a little different because this is on Q and this is on a closed interval, but they're much stronger and simpler in spirit than these. But these give you the gigantic theory. Um, these give you the gigantic theory of invariant maximality, which has a lot of manifestations that are important, and also make a lot of sense in regular real analysis. In regular real analysis. Okay, so uh, so that's what's happening here. So that's why there are now 9 chapters. Um, this needs to be seriously revisited. I was doing well with this. We were talking about this once. We talked about this for a few lectures. This will be totally revisited in light of everything else I know. Um, and this is going well. This was going pretty well. There's going to be a lot of stuff there. This I haven't really started, but I definitely want to put this in, and it's clear there's going to be some. See, you can kill all kinds of quantifier alternations get subsumed under game theory. That allows me to do a number of things I can't do normally. So this is very important. Number 9, although we haven't even started to talk about it. All right. Um, so uh, we're going to talk about this. This okay. This needs to be. I have to get into a different mindset to actually do this detailed reversal, and I think for next week I will probably not. I think for next week I will probably want to do this, which is I want to clean up everything in here so that that is no longer subject to any change, chapter 2. And then I want to talk about this. So chapter 4 is some powerful forms that use logical ideas like universal quantifiers or maybe even AE, I think. And I state statements that are considerably stronger, not logically stronger, stronger than the statements in here, the main statements. And I do that because I can get immediate consequences out of out of these stronger statements, which sometimes need the help of logical notions like universal formula or something. I can immediately draw conclusions of a purely mathematical nature, uh, immediately draw conclusions that I used to draw, like going to graphs or going to uh, uh, chains in the sense of any two distinct things are related, all those variants that people want to do. And also global restrictions, like given a relation, you can always find a maximal subrelation or maximal restriction, which is univalent or satisfying some condition, which is invariant, all that stuff. And there's like maybe 100 such variants that are perfectly reasonable to people, which you could list. And instead of going through those in a slog, trying to prove each one as each one is a consequence of what's in here, I simply, as simple exercises, you immediately see that they follow immediately without any work from chapter 4. And that's very important to have some tool like this because somebody's going to come up in regular math and say, I want to do something like that. I want to take a maximal blah, blah, blah in math. And is there anything like that you can do for me, Harvey? Um, and at least in the order invariant stripped down version, one can quote this, hopefully. So this is going to be important for at least in spirit, important for using this in general, using a variant maximality in math generally. Of course, there is this huge step that I don't dare think about, which is I'm going to do more than just order. One's going to do instead of just order, one is going to do have some additional uh, structure. So, in other words, there's a something called structured invariant maximality, structured invariant maximality, and which goes beyond just order. Though this whole book is just order. And then structured invariant maximality, if it really gets going, will revolutionize mathematics, of course. I like to make statements. I'm a little bit like Donald Trump. I make the strongest possible statement in, he does it in every sentence, and I do it in every less frequently. Uh, so, all right. So revolution of the whole of mathematics is not going to be done today, uh, but it's coming, of course. Just like AI is going to devour mathematics. Very maximality is is also going to devour mathematics. Well, anyways, uh, uh, don't take me too seriously. I'm the only one who takes me seriously. I know that. All right, so let's get into chapter two, revised with beautiful notation and everything. I defy the AI to be as good as me on making definitions. That, that's what I will. At least I'll be able to hang on to that. All right. So this chapter is called End Shift, End Equivalent, Invariant Maximality hyphen derivations. So introduction that's not been written. This has been a constant for some time. This is an old thing. This is just pure long-winded background on the notion of order equivalence and order invariance. And order theoretic is just bold-face order equivalence, order bold-face order invariance. And the quantifier eliminate the famous quantifier elimination for Q comma less than. So this is just beautiful background stuff that doesn't need to be looked at much. All right. Then we have maximality without invariance. In other words, no invariance. Well, we don't get any independence, but we do get. It's like the baby with the little toes in the swimming pool, right? This is what that's about. So, and by the way, I use chains and relations. I take it to be the crudest notion. That's the simplest one. Any two things, given x and y, x are y. I don't say given x not equal to y, x or y. Um, and that's just one of these variants that's taken care of and I told you in this uh, uh, logic-based thing in the chapter three, all those changes. So the notion of actual chain is the simplest possible notion one could possibly imagine of its kind. All right. So we have maximal chains in relations, which in pure set theory is equivalent to the axiom of choice over Z. And we have maximal chains in ordered invariant relations, which gives you a little subject of complexity theory, because an ordered invariant relation now is on Q. This whole chapter is on Q, and you can get a maximal chain that's in exponential time, and all that can be done in EFA. Yeah. So this is just all background material that it hasn't really changed. Now I have okay, so now the chapter is lead statements of invariant maximality. And just to emphasize to everybody, the seminal statement, right? The seminal statement. And now I know the seminal statement is, or I think I know it's going to be carefully done in chapter three. This statement is reversed to con SRP. And and the topic or name, if you want, is end shift inclusion. And this statement is perfect. This is a in the pantheon of 4,578 statements I have been pushing since 1967 when this project started. This is the culmination uh, in a different league entirely. I'm not talking about, though, explicitly pi 0 1. That's a little different category. We might find that the explicitly pi 0 1, because it's explicitly pi 0 1, is competitive. We don't know this quite yet, but anyway, so this is the seminal statement. You see, I want to make sure that anybody that reads the table of contents basically knows gets excited. I mean, that's a plan, right? Okay, and then then a modification, a strengthening of the seminal statement with end shift invariance, a modification or a further strengthening with n equivalent invariance. These are all first-rate statements. They're not quite as breathtaking, hopefully, as the seminal statement, and then emulators also, in some ways, yeah, some people, okay, so that was emulators that I used for high school students on the interval -1, 1 in dimension 2. Um, so emulators are still very important idea. Uh, uh, and a little different, but also a very serious candidate for a seminal statement is the emulator form. But I have to pick one. I don't want to confuse anybody with two seminal statements. It's got to be one. Okay. And I looked up what seminal means, so I'm okay. AI helps me with words like this. Um, okay, and then I show everything is equivalent to everything else. Okay, everything is equivalent to everything else. And all this stuff is equivalent to the seminal statement by soft proofs in simple proofs in RCA naught. Although they do get a little tricky. They do get a little tricky and time consuming, but they're basically totally elementary. They don't pass through any serious math logic methods. Now, this was the old statement that I claimed to reverse, which can be reversed by the old reversal, but it's a stronger statement. It's a stronger statement, and it is the right statement, however, for proofs. So I might as well prove a stronger statement when I get into proof mode. The rest of the chat, most of the rest of the chapter is in proof mode. Not all, but most is. Um, so the statement without less than or equals is, one of the lead statements. So uh, it's nice to have this because it's very intuitive and it's a stronger statement, and it's harmless to use this instead of the other when I actually do proofs. But when I do reversals, you really want the weakest statement, the best statement, the statement that's the most breathtaking. All right, so isn't that nice? Somebody can call their math breathtaking. Uh, of course, when you call your math breathtaking, everybody wants to know whether it's really correct. It probably means it's not. So I'm going to be an exception. Somebody calling their math breathtaking and actually having it correct. This is going to be a little bit novel, right? All right. Uh, so we actually prove it in dimension 1. Proving it in dimension 1, of course, is is uh, RCA naught stuff or EFA stuff, I mean, really, really basic, because you can give a complete description. You can give a very good description of all of the order invariant uh, relations in 2 dimensions. In other words, all the order invariant relations on Q squared. On Q, I'm sorry, all the order invariant relations on Q. That's just a simple inventory of 8. There are 8 of them. Everybody loves all of those 8. All right, then you go to dimension two where all hell breaks loose. And there's something I've got to tell you that I haven't said yet, which you're going to be very happy with. Okay, let me say that after I just point out. Okay, so we're gonna do this in two dimensions using omega one. Now, because I'm using this stronger notion of invariance, by the way, which in Q, and I'm going to back this up. I have to back this up in chapter three that I have the reversals. Because I'm using this stronger notion of invariance, it's just what the doctor ordered. Remember, in the old chapter four, in the existing monster reversal, I'll call it the monster reversal, I gave up and had absolutely no claims about the relationship between the dimensions. There was actually two parameters, k and n. In this thing here, I just used one parameter, k. Um, there was absolutely no claims about reversing anything with a specific dimension. I did, however, prove that there was some monster dimension and it didn't give any, the upper bound is, I don't know, 2 to the trillion or something, I don't know what. But there was a fixed K such that it was independent of ZFC. In other words, you did get a hierarchy, but I never said dimension three, it's independent of ZFC, which is something like I really wanted to do in the old reversal. Now, this reversal, because I'm using a much stronger notion of invariance, but much more mathematical also. Ah, but much more mathematical also. Because of that, um, it looks very promising. It's not like I've really gotten into this yet, but it looks very promising that I can actually do sharp reversals of fragments. That is, I would hope to show that this thing can't be proved in second order arithmetic, for example, this one here. Exact reversal might be a little trickier. Some sort of variant of Z2 is equivalent to con. I don't know if this is equivalent to con Z2. That would even be the best, right? But and without the less than or equals. Sorry, and without the less than or equals. So I'm now hoping to really get and really be able to get detailed reversals with this new situation. But the old situation is still very important. Local invariant maximality is a very important part of invariant maximality, but it's not necessarily the headliner right now. All right. So I go through 5 steps of the proof in omega one, where the transfinite combinatorics is well controlled. Uh, it's there in your face, so the mathematician will find this very friendly. It's pretty much in your face. Although there's some use of predicate calculus in here, which probably an exercise for a PhD student might be able to, or less below, might be able to get interested in how to remove the use of predicate calculus in here. There's some predicate calculus in here, which is I can't resist using. You can actually do a downward Skolem theorem, but just sort of say what you're downward doing mathematically, and maybe remove the logic, so to speak. But it's not a high priority for me right now. So, anyways, you have this transparent proof in the case of two dimensions. By the way, MCH means maximal chain. And when we go through some details, in the manuscript, I'm just talking about the table of contents, right? So, all right. Oh, OIR. So I changed some notation. OIR means order invariant relation. MCH means maximal chain. So order invariant relation, maximal chain, N equivalence, and Q squared. That's proved. Then I go to the arbitrary case where K is arbitrary, and now the large cardinal combinatorics, which sits in here, is vicious. It uses the SRP hierarchy or the subtle cardinal hierarchy, whatever variant you want. They're all equivalent right in here. So the mathematician will see the structure of the proof is the same, except instead of omega 1 combinatorics, one has kappa combinatorics. So it's all very clear. And then I want to get a little more detail about what I actually use for any fixed dimension. It's a K minus 2 subtle cardinal. And I only care about dimensions higher than 3 for that section because I've already handled dimension 2 and 1. 2 was omega 1 and 1 was nothing, right? So K greater or equal to 3. Um, and the large cardinal combinatorics is sensitive to the dimension that's used in there. So OIR means order invariant relation. Maximal chain is clear. This is the yeah, I haven't told you exactly what that is, but I did last time. But this is this variant that's stronger than the original without it. And N in Q, NEQ means N invariant equivalent. N equivalence, which is an equivalence relation, invariance. And the space is 2 Q to the K. All right, fine. After I finish all those proofs, there's a section called optimality of N equivalence. Uh, I haven't actually fully checked the claim, but you will see the beautiful claim at the end there, which is very satisfying, that N equivalence is the best you can do. Best is the very best you can do in anything remotely like this, okay? I do some logic bookkeeping. That's what this section is. That I'm actually showing such in such and such a system, I can prove the equivalence WKL naught plus blah is equivalent to blah. You know, I'm just making instead of informally talking about using omega 1 or whatever, I get specific about that. And I talk in general about what implicit pi 01 means. This is old material and falsifiability. In other words, my statements in this invariant maximality are falsifiable in the sense that you can a priori know that if they're false, they're provably false, and talk a little bit about how that interfaces with what goes on in physical science. So there's that. This is old stuff. Uh, this is still old stuff. This is old. Yeah, this style is old stuff. I have to restate it for everything. Okay, and then I get a little bit more serious about this less than or equal to form. And so I talk about invariant maximality on rational intervals. Invariant maximality so far up here is on Q, which is a rational interval. But what about all rational? So I prove that it works on a rational interval if and only if its left endpoint, which it may or may not contain, its left endpoint is negative. If and only if its left endpoint is negative. So that's the theorem in here. Invariant maximality works if and only if on a rational interval, if and only if the left endpoint is negative, that theorem. And then I link it to the old chapter 4. The old chapter 4 reversed this. Well, it was with cliques, but it's all equivalent. And this is changing the notation a little bit. If you remember this notation, this is a local invariance, and I'm on the interval minus 1, 1, if you recall. And it's just nice to know that this subject links to the rest of the book on local maximality. So this chapter is not really needed, but it just gives an alternative reversal that just uses the much harder reversal later. For this. Yeah. So this is an optional chapter that does say that this stuff is linked to the rest of the book in some sense. Okay. All right. So this stuff we don't want to talk about anymore. This was the background stuff. This was maximal chains and relations, which I told you about. This is just the definition of a chain and a maximal chain. Nothing new. And then this is the proof that's equivalent to the axiom of choice as expected. And then RCA naught, uh, uh, you can get that this is true for the in the countable case. And then in the finite case, just EFA is enough to formulate it and state it properly and prove it. And then there's this section. Okay, so this is a little more detail about now I bring in order invariant relations. And now here's the lead statement without the invariance, which means it's not exciting. OIR, ordered invariant relation, maximal chain slash Q to the K. Every ordered invariant relation on every Q to the K has a maximal chain. Okay, that's a pretty breathtaking statement, except that it doesn't take your breath away because it's proved by by the most standard methods, and it gives you an explicit maximal chain. It's not going to be. Yeah, just one second. Yeah, hi. Yeah, good. I think I got set up everything for you. Yeah. Okay, so housekeeping. That's invariant maximal housekeeping. All right, so uh, there's nothing going on here. Uh, uh, Order relation MCHQK is provable in EFA, but you can actually make a stronger statement. Every order invariant relation on every Q to the K has an exponential time maximal chain, and you can prove that. I'm going to give a detailed proof, not here, not right now. Okay, and then I want to go. I suggest you get more deep into this, but taking the uh, 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 yeah, go more deep into this in terms of computational complexity, yeah, which I don't touch, but it's probably pretty interesting. All right, now the lead statements. So uh, the seminal statement, refinements and invariants, all that stuff. I show they're all equivalent. Uh, and in this chapter, we're going to prove everything in sight is equivalent. Uh, we prove everything in sight in here. These statements are reversed in chapter 3. Thus, we conclude they're provably equivalent to con SRP over WKL naught. All right, the seminal statement, end shift inclusion. Okay, so as described last time, the end shift is defined as follows. You add 1 to all of the coordinates xi for which every xj greater or equal to xi lies in n. Period. That's the definition of the end shift. And the end shift of a set is the set of end shifts of its elements. Now, here's some illustrative examples of end shifts in dimension 3. And then when somebody goes through this, they know exactly what I'm talking about. This one, you don't do anything because there's because this tail, so to speak, is empty. In other words, there's nothing which has the property that everything greater or equal to it is an integer. There's no such coordinates. You don't do anything. But obtained from X by adding 1 to all. Well, if you don't add 1 to anything, you don't get it. You don't change the vector. Okay. And this one goes up by 1 because 2 is the only example. And then 0 and 2 are both examples, so they get bounced to 1 and 3. And minus 1 is just not touched. Negative numbers certainly won't be touched. Okay, so there we are. Now we come to the seminal statement, which is supposed to take your breath away. So here's the terminology: OIR, ordered invariant relation, maximal chain, the end shift under inclusion, and QK. So it says every order invariant relation on every Q to the K has a maximal chain containing its end shift. Let me repeat. Every order invariant relation on every Q to the K has a maximal chain containing its end shift. So that's supposed to be the seminal statement. In section 2.9, we prove this statement going way beyond ZFC. And now we want to talk about end shift invariance, which is stronger. And this is just the notion of invariance under a function, which uses an ambient space, But right in our case right here, the ambient space is not used because the end shift maps my space into itself. So it's even the most trivial notion, the most trivial direct notion of invariance under a function because it maps the ambient space into itself. In local invariant maximality, where I'm on intervals, I've got to use the ambient space being in some closed interval. There, I actually do use the ambient space component in the definition of function invariance, but not here, which is nice. So end shift invariance just means what you expect. If and only if for all x and q to the k, x is in S, if and only if the end shift of x is in S. We now have two statements, the first from section 2.4. So I'm just being very gentle. Every order, this is the seminal one, has a maximal chain. Every order invariant relation on every Q to the K has a maximal chain containing its upper shift. And then the next one, the variant is every order invariant relation R on every, no, I don't need this. I need this some later. I don't need this. On every Q to the K has an end shift invariant maximal chain. Okay. Now that's obviously stronger than just inclusion. I mean, we show a later chapter, the later section here that they're all equivalent. Note the suggestive use of this and this. I means invariance, and notation make a big difference. And I indicating inclusion and invariance respectively. And the trivial direction of this is obviously the trivial direction. The converse will be proved later. Now we have another variant, and an equivalent invariance. We've been already using equivalence invariance with ordered invariant subsets of the QK. In other words, we already have order invariant, just plain old order invariance we've been using. But this is new. Here, the relevant general formulation of equivalence invariance this is general invariance with respect to an equivalence relation. So in this book, we have three different kinds of invariance. One is invariance with respect to a function, invariance of a set with respect to a function, invariance of a set with respect to an equivalence relation. And in the local invariant section, in the later part of the book, not here, we have a invariance of a multidimensional set with respect to a one-dimensional map. That's the local theory. Okay, one-dimensional map. Not sure local is the best word for that, but I'm going to use it. And that we don't talk about that today. I mean, we don't talk about that in this front of the book that we're doing. So the field of relation, what does it mean to be reflexive? What's an equivalence relation? All that stuff standard. And then we have the definition of invariance. Definition of invariance. Okay, note that X acts as an ambient space. In this chapter, we won't even need ambient space because the equivalence relation is defined on all of Q to the K. So we're going to use n equivalence only on Q to the K for equivalence invariance. Section 2.13 is, I think that's the section, I mean, it may be misnumbered because of number changes. I think that's the one where I talk about doing stuff on intervals or something. Yeah, but basically just as an afterthought. Yeah. So thus we are in the simplest situation where the equivalence relation is on the ambient space, and we have to define an equivalence. So we this time we bring in the notion of tail. So a tail is the part of X consisting of the Xi for which every Xj greater or equal to Xi lies in N. And X and Y are N equivalent if and only if X and Y are order equivalent and agree off their N tails. Now, the nice thing about the N shift is it doesn't mention order. The N shift is a purely mathematical, is a purely non-order theoretic notion, the N shift. But the N equivalence relation is not. The numbers in the N tail of X are held in place. When I talk about agree off their N tails, I don't mean, I mean that the N tail is held in place. It's a partial sequence, so to speak. Now notice that n shift of X is the result of adding 1 to the N tail of X. So it was convenient to define the N shift directly without first defining the N tail. It's much better to do that because it's easy. But in the case of N equivalence, it's kind of awkward. So I define N equivalence first by defining the N tail first. But now you see that my seminal statement should be N shift involving N shift rather than N equivalence. We don't want any possible use of the brain, serious use of a brain to understand my seminal statement. This is important. And then we just define yet again N equivalence, N equivalence invariance, it's called. If and only for any N equivalent X and Y, X is in S if and only Y is in S. So now we have three statements. See, I try to baby everybody so that they feel like they can that this is all trivial. You have to give them the feeling this is all completely trivial stuff. So we have three statements. The seminal statement, every order invariant relation on every Q to the K has a maximal chain containing its N shift, and every order invariant relation on every N, Q to the K has an N shift invariant maximal chain. And finally, every order invariant relation on every Q to the K has an N equivalence. Let's do this right. An equivalent. That's an equivalent invariant maximal chain. That's why it's NEQ. And then with a trivial lemma, you get completely trivial chain of implications here. Totally trivial. Yeah, all that stuff down there. Yeah, yeah. In section 2.5, we'll prove all these equivalent, all the converts. Now, emulators are very important also, and they're important for gifted high school. So S is an emulator of a finite set, if and only if S is contained in Q to the K, and every element of S squared is order equivalent to an element of E squared. Every element of S squared is order equivalent to an element of E squared. S is a maximal emulator, if and only if S is an emulator, which is not a proper subset of any emulator. And then our statements with emulators. All right. I'm going to add some material. I'm going to add some comments in the text that some readers may choose to feature these three rather than the first three. It depends on the audience, something like that. All right, and we have the completely trivial chain of implications. And then we prove that all six of these statements are equivalent. There they are again. All right. And then we verify the circular chain. This one implies this one implies this one. The first three are trivial. The first two implicated trivial. Implies this one, which is non-trivial, implies this one, which is non-trivial, implies this one, which is non-trivial, which this one, which is trivial. And this is a circular chain, right? It's a circular chain. So they're all equivalent. Okay, and then I actually go through this. I'm not gonna. I had to come up with an intermediate statement. I had to come up with an intermediate statement in this that's not part of the agenda in order to pull off some of these statements. Yeah, so I don't want to get into too much detail with this. Yeah, so I do the circular equivalence chain. And then I do one more thing, which is that higher dimensions give you lower dimensions, which is expected and easy actually. Uh, yeah, which is important to know at least. All right, now this is the strengthening that's very mathematical um, that can be reversed using the old hard reversal, the old much harder reversal that comes later in the book. I'm actually careful to. In fact, I will say this in the preface of the draft of the book, or maybe even in the final form. I'm not sure. I'm careful to talk about what would happen if something went wrong with the details in these parts of exactly how to recover slightly weaker results and stuff like that. So I am sensitive to that because things are very delicate, right? I don't want something to go wrong and then people think that the book is wrong or something. That so for example, if there was something wrong with chapter 3, which I just that was the big push today that I was talking about, then I would have that this was the statements with less than or equals were independent instead. Like last time I was claiming last week. But it's much better that I have what I'm claiming now. All right, so every order invariant relation R on Q to the K has an N equivalent invariant. I think I really don't want to use that. S, where each S restricted to less than or equal to N is a maximal chain in R restricted to less than or equal to N. So this, and then it's easy to prove that this implies the original one without this. You have maximal in now this is obviously a very natural mathematical move that's probably made in mathematics in some sense, all through mathematics in some sense. Uh, sort of, kind of a localization thing. I call it initialization because I don't want to overuse the word local because I'm using local invariant maximality. So I don't call it localization. I call it initialization because these are initializations of the set and the function, right? I'm initializing, going in to initial segment. And then uh, the proof in the case of dimension one, you just list all the 8 and check it. And then in omega 1, uh, we don't need to talk about this too much. I've talked about it in one form or another, maybe 10 times in one form or another, right, in this lecture series. uh, But anyway, so we don't have to get into this too much. I mean, I might say, we might go before I finish, before we get into chapter three, I might actually, dig down a little bit further, particularly when I have it all polished up, um, how these proofs go. But they're not nothing surprising because we've done so many things like it. Um, all right, so here is the optimality claim. And this actually, I put a question mark here because I haven't had time to get into the details of this. But I'm pretty sure this is right. So n equivalence on q to the k, at least I want this to be right. Uh, n equivalence on q to the k is a subset of q to the 2k, right? Because any relation on q to the k is a subset of twice the dimension. That's first order definable without parameters, obviously, first order definable without parameters. Uh, because you can quantify over n. You see, you can quantify over n in order to pick out what the n tail is. So this is pretty clear. It's actually much better than first order definable. Um, I mean, it's low level first order definable, but I don't think I need that. I think I just need to quote that it's first order definable, and I get that n equivalence is the maximum equivalence relation, first order definable over q less than n, with parameters that can be used with parameters. No, without I'm sorry. Yeah, this is bad mistake. Without parameters that can be used for invariant maximality. And I'll be more explicit about that. That means you take any of my statements I've been talking about. N equivalence is the maximum one. Maximum one. It's the union of all ones that work. That's the best possible result. It may turn out, I mean, this was happening when I did intervals. Intervals have a symmetry that all of Q doesn't when you reverse the order, because I was doing it with endpoints. Um, I remember when I was doing stuff like this before in that different context, I needed there were two maximum ones. One was uh, one was opposite of the other, but I think that doesn't happen here, which is very nice. But anyways, I have to go through and actually do this. That's probably something that I will also do next week, in addition to talk about the reversal. I think I need to talk about this, and also this. I've got to talk about this. So these two things probably next time. This, uh, and at some point I want to talk heavily about the reversal, which again I is 10 times easier than the hard reversal in chapter 4 because of the stronger invariance I'm using. So logic based, this is designed to prove far-reaching extensions of the statements in chapter 2, which allow for numerous applications far beyond invariant chains and invariant emulators, e.g. chains not equal to, meaning any two distinct elements are related. Um, and it chains not equal to. In other words, any two things are not related, or any two things, distinct things are not related, or cliques in simple graphs, independent sets in simple graphs, dominators in simple graphs, various kinds of subrelations and restrictions of order invariant relations, e.g., maximal univalent subrelations, maximal univalent restrictions, maximal bijective subrelations, maximal bijective restrictions. All of these statements are going to be easy applications of these more powerful invariant maximality statements. Yeah, so this is a very good situation. It saves me a lot of boring, detailed work. Uh, Although this doesn't show that I get equivalence when I make these small changes. That I get only because this proves them and that they can be reversed. Yeah, so there's probably something. it's probably trivial that these variants reverse, or fairly trivial that these, because they imply the old original ones or something. So there's something here, but that'll all be handled in chapter 3, and that's icing on the cake. I think there's nothing else here. All right, so Andreas, I think I'm done here.